So now finally, as a last modification to our FastSLAM algorithm, we're looking for a way to get rid of those landmarks that appear at some point in time, but then are not measured subsequently and still stay in the list of landmarks in our particles. Now here is an approach to deal with those spurious landmarks. So when our robot observes a landmark for the first time and it initializes a new Kalman filter for that landmark, it would also initialize a counter and set this counter to 1. If our robot moves on and observes this landmark for the second time, we will increment this counter each time we observe this landmark. And so this count value is a measure of confidence for the existence of this landmark. Now what happens if we move on? Say here, the field of view of the laser scanner is like this, so it can't see this landmark anymore, and so we have to decide if we shall decrement that number or if we shall leave this as is. Now if we would decrement it, the following would happen. After this movement, the count would be 2, 1, and 0. Or even -1. And so we would remove the landmark when its count is below 0. Now using this strategy would mean that we forget our landmarks if we don't observe them regularly. Now this looks good at first sight. However, remember the situation in our arena. We started here and going along here, we observed some landmarks, quite for a number of times, and then being here, they're clearly out of sight of the robot. So after a while, we would forget those landmarks. However, later on, we come back, and the landmarks would be in our field of view again. However, at that moment, we would have forgotten them, so we would have to reinitialize the landmarks, and all the earlier measurements, which have led to a precise position of the landmarks, would be lost. So we will adopt the following strategy. If our robot sees the landmark for the first time, it initializes it and sets our landmark counter to 1. Now later, if the robot does not report that it sees this landmark, although the landmark is within the visibility range of our scanner, we will decrement the count. However, if our robot is somewhere where the landmark is not within the visibility range of our laser scanner, we will not decrement the count. Now we will use a simplified method to decide whether a landmark is within the visibility range of our LiDAR. Namely, we know the minimum and maximum bearing angle of our scanner, and we will consider any existing landmark which has a bearing angle within that range as being visible by our scanner. Now this oversimplifies things a little bit. For example, as you know, our landmark detection works by detecting peaks in the scanner data, and so certainly if a landmark is, for example, at the beginning of the scan measurement, like this landmark here, our method would fail to detect the landmark. Nevertheless, our geometric test would say that it is within the range of the laser scanner. And so for our simplified test here, we just don't care about this. Also, we don't handle occlusions correctly. For example, if there's one landmark here and another landmark here, then our LiDAR would detect something like that, which means our function will only return this landmark, although our criterion would consider both landmarks to be visible. And so we also don't care about this case. Technically, we will handle our landmark counter as follows. So at a certain step of our FastSLAM processing, a certain particle has collected a number of landmarks. So using the bearing angle criterion, we will identify the landmarks that are visible and decrement their counters, whereas we do not touch the counters of all landmarks which are not visible. Now if we observe a landmark, so we obtain an observation and assign it to a certain landmark. Using our maximum likelihood assignment, we will add +2, so that for those landmarks, we will indeed increment our counter by 1. Whereas for the landmarks we do not touch anymore, this results in a decrement by 1. And for any landmark which we observe for the first time, we will directly set the counter to +1. And after initializing the new landmarks, we will loop over all the landmarks of a particle and test if their count is smaller than 0. So say if the previous count was 2, then it is 2 and the landmark stays. If it was 0, the result is 0 and that stays 2. But if this was 0, the result will be -1 and the landmark will be deleted from the list of landmarks of this particle. So now let's program this. I prepared SLAM10F counter for you, and this is mostly the same code as in our last exercise, with some modifications. Now let's first have a look at the update and compute weights function in our FastSLAM class. So there are 2 modifications here. Now in the loop over all particles, we had a call to a function that decrements the landmark counters of the particle. So it does the following. For each landmark that should be visible to our laser scanner, it decrements the counter, and for any landmark outside the visibility range of our laser scanner, it leaves the counter as is. Then here is our loop overall measurements, and this is not modified from our previous solution. But here, after computing all the weights and updating the landmarks, we call remove spurious landmarks, and this function will remove any landmark which has a counter smaller than 0 from the list of landmarks of that particle. Now these are the modifications in our filter class. Now let's have a look at the modifications we'll have to do in the particle class. So the first modification in the particle class is, in the constructor, we now set up a list of landmark counters, which is initially empty. Below this, there's our usual code, and you will have to insert your previous code here and there, and all the places are marked as usual with that sign. And so here in update particle, there's the first modification you'll have to do. First, insert your previous code, but then modify this code as follows. As you know, after computing the likelihoods, your code has two alternatives, namely initializing a new landmark, in which case you'll have to append 1 to the list of landmark counters, or updating an existing landmark, in which case you'll have to add 2 to the corresponding landmark counter. And I just explained why this has to be 2, namely because we decrement the counters of all visible landmarks in advance, so we have to add 2 in order to end up with a +1 for a landmark which is in the visibility range of the scanner and is indeed observed. And then you'll also have to implement those two functions. The first one decrements the landmark counters for any landmark that is visible, and the second one removes any landmark which has a negative landmark counter. Now after you program this, run it and it will produce the file fastslamcounter.txt. Now load this and you should obtain a result that looks similar to this one. In the beginning, the covariances of the landmarks get smaller, and then our particles travel along the trajectory. But now, here we encounter an undesired effect, namely this landmark that has been observed multiple times before is now occluded by this landmark, and so its counter is decremented, and this results in the landmark being removed, at least for the particle that we pick and whose landmarks are displayed here. So shortly after, the landmark is observed again, so a new landmark is initialized, which you can tell from the large arrow ellipse, which gets then subsequently smaller. However, note that our modification has solved our previous problem, so even though sometimes spurious landmarks appear, they are usually removed shortly after, so that overall we get a pretty good result. So now please program this.